All right, so looking at the periodic tables, we have the plus one, for example, the H plus and we have Li plus, Na plus. And so what are the names for these things? So the names for these would be like the hydrogen ion, etc., lithium ion. And then we have the M2 plus. M2 plus, an example of this would be something like, let's go with, which would do probably magnesium, Mg2 plus. This would just be magnesium ion. Magnesium ion. Now, we go into the transition metals after that. Periodic table here. All right, so we have our alkaline metals, all plus one, then our alkaline earths, all plus two. Now, normally when we go into this region, we call these what? The variable charge. But it turns out not all of these are variable charge. So for example, zinc, cadmium, and silver are fixed charge. But did you know scandium and yttrium are fixed charge too? What would you guess the charge on scandium is? Scandium is always plus 3. Scandium is plus 3. And so scandium 3 plus, this is a scandium ion. We don't use a Roman numeral for this because it's just a single charge. And then next to scandium is yttrium, which is 3 plus right below it, which is the yttrium ion. Is that 1 T, 2 T? Yttrium ion. Scandium is pretty common. Yttrium was common for a while because that was in some superconductors had yttrium in there. Okay, then we go on to the variable charge here. The variable charge species, like which ones? Like chromium. You know, what's the charge on chromium? Chromium 2. This would just be an example. Roman numeral 2 or chromium 3. Chromium, Roman numeral 3. Here. So we have variable charge. And then we have that little elbow of fixed charge here. And that is the zinc, which is just zinc ion. The cadmium is cadmium ion. And silver. Silver is always plus 1. So this would be silver. So this would be fixed charge here. So we have these fixed charges are boxed, the variable charge here. Now, the variable charge is going to sneak into the what we call the main group here. The main group is these first two for this block, and then this last 6 columns here. This is the main group. And one of the main group are fixed charge, like carbon, nitrogen, oxygen, but the ones down here are variable charge. So the variable charge range is like this here in the periodic table. And so anything in this range, except this little island here, you have to use a Roman numeral. So for example, lead, what's the charge on lead? 2 and 3, or 2 and 4. Tin's the same, 2 and 4. And so arsenic is variable charge as well. And so variable charge creeps into the main group. So we have some fixed charge up there. Now, for the fixed charge up here, let me continue. This is going to get kind of long, but we have B. Now, B, what would you expect the charge on B to be? Well, B, I'd expect the charge to be like aluminum. You know, what's the charge on aluminum? Aluminum is fixed charge at 3 plus. And so this would just be the aluminum ion. But boron is, we don't see the boron 3 plus ion that much. So we'll just leave it like that. Actually, let's continue here. All right, carbon though we do see. You know, carbon, when we get to carbon, what do you think the charge on carbon is?
4 plus.
It could be 4 plus or it could be 4 minus. And so it's a little bit tricky. 4 plus or 4 minus. It's right in the middle there of the periodic table. Boron we'd expect to be a 3 plus, but when we see it, it doesn't form a regular ion. So what we do is we just do this. We write like a Roman numeral here. So like carbon 4 plus here, this one we would say carbon Roman numeral 4, indicate that. And carbon with a 4 minus. Now carbon with a 4 minus, do you know the name for that? The name for that would be carbide ion. Now carbon with a 4 plus is just called carbon, you know, just like all the other, but we don't, you know, you can call it carbon 4, which is fine. Carbon Roman numeral 4. It's a little bit different. And so carbide ion, and then we have some others. So for example, boron, you know, we might expect boron to be like boron 3 plus, right? Because it would be like aluminum here. But we'll map out some more ions here. So for example, here this would be monatomic, but we have polyatomic too, such as borate. You recall borate? Borate would be B.
3 minus.
Okay, how many oxygens in borate? BO. What group is boron in? The number at the top column. 3. So you see it's 3, so it's going to be 3, 3. So this is borate. So we have the carbide ion, this is one you should know, and then we have the carbon 4. And then we also have carbonate. What is carbonate? CO3, 2 minus. Now we want to memorize the 8s. Why do we want to memorize the 8s? The polyatomic anions that end in ATE. The reason we want to memorize the 8s is because the ites are easy to derive from the 8s. The ites will have a different number of oxygens. You know, how many oxygens will the ites have? Well, we don't know the exact number, but we do know it's going to be 1 less than the...
So with that, basically, what binds with an ozone, correct?
It's not an ozone. I mean...
Is O3 ozone then?
O3 is ozone, that's correct. But ozone, it looks like this. Ozone's going to have 3 oxygen atoms bonded together in a line. But when we look at borate, the boron's stuck in the center. So the boron's here, let's say, and then we're going to have oxygens stuck on top of those. And so ozone would be like this. And so what we don't have is we don't have a boron atom stuck to an ozone molecule. What we have are the 3 oxygens are separate, and then the boron's stuck in the center of that. And so this thing does not behave like ozone at all. You know, it just so happens that it has 3 oxygens, but it doesn't mean it's ozone. It's like CO2. You know, CO2 happens to have 2 oxygens, but it's not like an O2 in there, like you're breathing O2. The oxygens are actually split apart. It's just a ratio. So, the same thing here. And so we'll have carbide ions and then we'll have carbonate. The reason we want to memorize the eights is because we can derive all the others. You know, for example, carbonite. If there's carbonite, it would be CO2 minus, 2 minus. So it would have the same charge, so it would be CO2, 2 minus, if there is a carbonite. If there is a hypocarbonite, you know what hypocarbonite? Hypo means one less. And so one less than I8 would be CO with a 2 minus charge. If there's a percarbonate, it would be CO. Percarbonate would be CO4 with the same charge, 2 minus. And so we could derive all the others. It doesn't mean that they exist. So percarbonate doesn't exist, you know. Just like carbonite and hypocarbonite aren't common. But sometimes they do, and then we can derive them based on that. And so if we go from carbon to nitrogen, nitrogen should have a 3 minus charge here. And so if nitrogen has a 3 minus charge, we call it nitride. So we want to know that. And then we also want to know the oxyanion for this, nitrate. So nitrate would be what? NO. Not NO4. Did you guys memorize the pattern from the periodic table? No? NO3. What's the charge? NO3 minus. And so this would be nitrate. So this is nitride, nitrate. Now what's often confused with nitride is nitrite. What is nitrite? NO2 minus. And so nitrite, we don't have to memorize nitrite. We don't have to memorize nitride. We don't have to memorize nitrate as long as we know the pattern here. And so this is trying to reduce the amount of memorization that we have to do. And so we should be able to derive these based on the pattern in the periodic table. So we have nitrite. Nitrite's very common. And so this is nitrite. Now we have to keep in mind, when we have a D here, it's usually a monatomic element. Not always, but typically is. When we have a T here, it's a polyatomic oxyanion. It has oxygen in there. All right, after nitrogen comes oxygen. And so oxygen's charge typically is 2 minus, and we call it, what's the name of this? Oxide. As far as oxyanions go, they're not here. I'm not going to worry about them. And then after oxygen comes fluorine. The charge on fluorine? -1. Okay, then this is going to be fluoride. Fluoride is commonly misspelled. Fluoride is FLU. A lot of people spell it FLO, like flower. FLOU. FLUO. Fluoride. We have the fluorate ion. What is the fluorate ion? FO3 minus. This is fluorate. Now, not everything forms the series that is one less, one less. So let's go with the series here. That means fluorite will be what? So this is the way I think about it. Fluorate, if I know fluorate, FO3 minus, then fluorite's easy. Fluorite will be FO2. Charge? Minus. Okay, if that's fluorite, then hypofluorite is what? Hypofluorite would be FO minus. Hypofluorite does exist, fluorite exists. And then we wouldn't say per hypofluorite because that would just be fluorite. And we wouldn't say per fluorite because that would be fluorate. We'd have to say per fluorate, and that gives us something new. So perfluorate is FO4 minus. And so this would be the series. All right, let's look at some more of the ions just to review. What do you think aluminate is? Well, that might be a little trickier. I didn't ask you to memorize that because I asked you to memorize the one next to it. What's next to aluminum? The reason I asked you not to memorize aluminate, instead I asked you to memorize silicon. Well, actually, silicon can do the same thing. What do you think the charge on silicon is going to be? Either like +4 or -4. And so it's going to be, +4 is tricky because +4 has extremely high charge. +4 is thought of as very, very reactive, because of the high charge. And so electrically it's going to be not as stable. So we typically write it in Roman numerals, whereas things that are more stable, like aluminum with a +3 charge, there's no problem. And in fact, most aluminum found in nature is +3. So silicon 4, or what's the other charge on silicon? Or 4 minus. And so we call this silicon 4, the first one. When you start getting these high charges, we typically use Roman numerals to indicate that they have to be stabilized by something. And so silicon 4 is usually stabilized with having some negative charge next to it from some other atom. And then this one's okay. This one would be called, if we had silicon with a 4 minus charge, what would we call it? Silicon with a 4 minus charge would be called what? What did you call, did I name it? What did we call carbon with a 4 minus charge? Carbide? What do you think we call silicon with a 4 minus charge on it? Silicide. So this is the silicide ion here. But we also have an oxyanion ion. Si, how many oxygens on silicon? And so this is why I asked you to memorize silicon. I asked you to memorize boron and silicon. Silicon has a, well, what group is silicon in? It's in group 14 or 4. 14 or 4 means 4-4. See, there's minimal memorization you have to do as long as you memorize. So, 4-8, the anchor for the 3 oxygenates. And this one, silicate, which is the anchor for the 4 oxygen. Okay, next to silicon is phosphorus. So phosphorus, we have the 3 minus ion, which is common. What would we call phosphorus with a 3 minus charge on it? Not phosphate, because the 8 tells us, yeah, this would be phosphide with a D. D. Phosphate, what is the formula for phosphate? PO4, 3 minus or 4 minus? 3 minus. So this is phosphate. What should phosphite be? PO3 with a charge of 3 minus. Phosphite. There's no perphosphate and there's no hypophosphite. This one. So we got phosphate. And then next to phosphorus is sulfur. So S2 minus is a fixed charge. What would that be called? This is sulfide. What would sulfate be? SO4, 2 minus, that's sulfate. What would sulfite be? SO3, 2 minus, this is sulfite. Sulfite's very common, so we'll do that. What would thiosulfate be? Thiosulfate. Yeah. S2O3, 2 minus. This is thiosulfate. Remember, thio means what? Thio means to replace an oxygen with a sulfur. They're in the same family, so it doesn't mess up the charge. And so we just take one oxygen off sulfate and add a sulfur in its place. So that gives us S2O3, 2 minus. And so by learning the patterns, you can avoid a lot of memorization. Otherwise, you're just going to have to memorize all these. And so next to sulfur, we have chloride, but that's part of the other grouping here. And so it continues down. Now I asked you, what would you guess aluminate ion is? Just take a guess. Well, we know the aluminum ion. Aluminum ion is just Al3 plus. Aluminate? ALO4. ALO4. 3 minus, 5 minus, 4 minus. That, this is what we see about patterns. So we try to look at the pattern, then we can try to make predictions based on the pattern, right? And then see. But sometimes if we have some more in-depth structural knowledge, then we don't have to worry about it. And later on, when we get into the structure a lot more, then we can figure out, what illuminate should be, as far as it goes. But you could take a guess, and let's see how we did for illuminate. ALO4. You see it? ALO4, 5 minus. ALO4, 5 minus screws up my little memorization pattern. And so this is why I anchored it with silicate rather than illuminate, because silicate's easy to remember. Silicate is what? 4, group 4. Borate is easy to remember. Borate is 3, group 3. All right, so we got those ions. So we could have figured out illuminate. I mean, if you're looking at the charge, how the charge drops by 1, and so it just makes sense that it would be a 5 minus rather than 4 minus in this particular case. Okay, then we have the others. The others are just straight memorization. And the others, we can get from the pattern, but the others we don't. So for example, chromate, etc. Mercury, 1. I mean, there's no pattern. This is straight memorization. Mercury, 1. Ammonium. Chromate, dichromate. All right, so let's get some practice naming some compounds here. Let's do some from your homework. What I'll do is I'm going to do the black ones. That way you have the blue ones for practice. We'll go through the black ones pretty quick here. This black and white. I don't know why this is black and white, but write the chemical formula of each of the following. The yellow spheres represent fluorine, and the green spheres represent chlorine. Fluorine is written last in these formulas. And so these are two chlorine atoms, or is that fluorine? 2 fluorine atoms. 2 fluorine atoms put together in a single unit, we'd call that what? Diatomic fluorine, or F2. F2, the fluorine, molecular fluorine. This is chlorine with a fluorine. If it's chlorine with a fluorine, then that's called a binary compound. And it's a binary compound made up of nonmetals, so it would be a molecular compound. And so we name one first and then the other one second. So they're telling us to name chlorine first, followed by fluorine. And it turns out we usually put the ones at the top right of the periodic table, the smaller ones, second. And so this is what we call chlorine monofluoride. This would be called chlorine. And how many fluorines do we have? 3. So that would be chlorine trifluoride. So this would be chlorine trifluoride molecule. This one would be chlorine with, it looks like 5. Let me see if there's one stuck on the bottom. There isn't. There's just 5. So that would be called chlorine pentafluoride. And so this is for molecular compounds. All right, that's number 2. Let's go to number 4. Here. Write the chemical formula of each of the following. A compound made up of a crystal with 2 particles coming from chromium atoms for every 3 particles coming from oxygen atoms. So this is going to be a crystalline structure. It's going to consist of chromium and oxygen in a certain ratio. If it's a crystal, then we call it a crystal lattice. And a crystal lattice, does it have a distinct end or no distinct ending? No distinct ending. So for every 2 chromiums, we have how many oxygens? It says for every 2 chromiums, we have 3 oxygens. Now, again, this is not ozone, but it would just be oxygens like this. So we'd have a chromium, oxygen, chromium. And then we got like 3 oxygens for every 2 chromiums. So it looks something like this. But this we wouldn't call a molecule because this is part of a lattice. And if it's part of a lattice, then the lattice just continues. And so it would continue on like this. In all dimensions, including coming out of the board and going back in. And so when you look at this, how do you write the formula for this? How you write the formula for something like this is you look at the simplest ratio. So for example, it depends on how many of these black ones we have and how many blue ones. But the simplest ratio turns out to be 2 chromiums for every 3 oxygens. So this is called the simplest whole number ratio. Which is given the name, the empirical formula. And so we just break it down. And so we got 2 chromiums for every 3 oxygens. And again, this forms a lattice. In this case, we call it an ionic lattice because this lattice is going to be made up of ions. What are the ions that are making this one up? Now, we've got to figure out the charge on these. To figure out the charge on it, we know chromium is variable charge, right? And so the first thing is, well, chromium can be a 2 plus or 3 plus. We don't know. But oxygen is not. Oxygen is fixed charge. What is the charge on oxygen? Oxygen is a 2 minus. And so what we have is we have 3 oxygens and 2 chromiums, so we need to balance out the charge. To figure out the charge, we get 1, 2, 3 oxygens here, and then chromiums, we have 1, 2 chromiums. And so the total positive charge has to equal +6 to balance out the total negative charge. So this would be the total here. And so if we got -6 total charge, what is the chromium charge here? Yeah, each of these must be 3 plus. Otherwise it doesn't work. And so what's the name for this? Well, it's an ionic compound, so we use a different name. Do we call this dichromium trioxide? Even though it is binary. It is binary, but we only use the di-tri tetra prefix if it's a molecular compound. This is an ionic compound. How do I know it's an ionic compound?
Which one is metal and
Yeah, metal and non-metal. Tells you right on. And so how do I name this? Well, ionic compounds, we need to name the cation. So we figured out what the cation is. The cation is chromium. It's got to be 3 plus. Otherwise, charges don't balance. And so the way we name this is we call it chromium. This is the name of the cation. But since it's variable charge, we have to add the Roman numeral 3. This is all one word, chromium 3, then space, and then the second word is oxide or trioxide. Oxide. But we don't need the tri here because we can figure out the ratio based on the charge balance. And so for ionic compounds, we do not use the prefixes.
So if it was CR4O6, it's still the same. So
Yeah. Yeah, if it's CR4O6, it's still the same. In fact, when we build up this lattice, I have 1, 2, 3, 4, 5, 6, 7, 8. I get CR8. It's always got to be in the same ratio. And so empirical means the simplest whole number ratio. It could be anything like CR200, O300. Depends on how big the crystal is. Because the crystal doesn't have a distinct ending. Eventually you're just going to end the crystal and that's it. And so some people try to grow bigger and bigger crystals with this stuff. And that's the ending of the lattice. And so since we can have variable size, what's the smallest we can have? The smallest we can have is CRO. Is that the smallest? CRO? No, that's not the smallest because the charges are not going to balance. I mean, if chromium is a 3 plus and oxygen is a 2 minus, then this is not neutral. This is going to have a net +1 charge, which means it's not stable. It's like static electricity. Well, it's not going to be stable. It's going to discharge. And so the simplest ratio is the 2:3. This ratio is much higher, but it's the same. Much higher numbers, but it's the same ratio. Sorry. All right, let's take a look at 4B. Compound made up of a crystal with one particle coming from barium for every two particles coming from chlorine. So in other words, one barium and two chlorines. Can you do that one for me? One barium, two chlorine. What would you call it? Again, this forms a lattice, like this. And so we look at the simplest ratio. The simplest ratio is going to be one barium and two chlorines. So it's just this, BaCl2. Again, it's what we call an empirical formula. This does not form molecules. So it's just BaCl2. And what would the name be? Yeah, this would be a solid. Same thing with chromium. It's a solid. Most metal oxides, in fact, all metal oxides, like iron oxide, lead oxide, all those are solids. Non-metal oxides, like carbon monoxide, carbon dioxide, are typically gases. Yeah. Some are solids. What's the name of this? Barium chloride. Barium's a fixed charge, it's 2 plus, and then we need 2 chlorides. That balances out the charge, just in a ratio here. Barium chloride. A lot of people do this to figure out the charge, as was mentioned earlier. Some people will do this. But sometimes it doesn't give you the right charge. Sometimes you have to adjust it a little bit. Get the right charge. So an example of where it wouldn't give you the right charge would be alpha. And so I like to do it differently. Alpha would be aluminum phosphate. But anyway, let's continue with this. C, the compound made up of molecules. These molecules are going to have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. So now this is not a lattice. This is carbon with 12 carbons, 22 hydrogens, and 11 oxygens.
Is that sugar or something?
Yeah. This one we don't use. Do you use the prefix? Do you know the prefix for 12? No. This is not a binary molecular, so we wouldn't be using prefixes for this. This one a lot of people recognize because it's just table sugar. It's called sucrose or table sugar. There are lots of different sugars though. There's sucrose, glucose, fructose, etc. And so this is one you just know the common name. A lot of people just memorize it. The compound made up of molecules with 3 hydrogens, 1 phosphorus, and 4 oxygens. Three hydrogens, 1 phosphorus, 4 oxygens. Now, when you see this, do you recognize this? Yeah, that's phosphate. What's the charge on phosphate? It's 3 minus. And these 3 hydrogens are like this. And so this would be called hydrogen phosphate. Or it's more commonly known as phosphoric acid. And so we'll talk about naming acids in a little bit. I just want to start with the ionic compounds right now. Let's take a look at number 6. Write the formulas of all elements that exist as diatomic molecules under normal conditions. You guys already have this memorized, right? 7 diatomics. Let's skip that question. Some time. Number 8. Given names, write formulas. Given formulas, write names. So, germanium. What's the symbol for germanium? GE. Is it a diatomic or anything like that? No, it's just GE. It's solid. It's a semiconductor. Fluorine. Yeah, that's a diatomic, so we call it what? F2. But it's ambiguous, right? Because they might be talking about atomic fluorine, or they might be talking about elemental fluorine, or diatomic fluorine. Depends on the context of the question. Argon. This is atomic. That would just be AR. Gallium would just be GA for gallium. All right, let's go to number 12. Actually, no, skipped one. Let's go to number 10. Number 10 is black. O2 is called oxygen or molecular oxygen or diatomic oxygen. All 3 are usually used to refer to O2. Ca, Ba, Ag. Ca is fixed charge. What's the charge on Ca? Ba and Ag. Now, if I said calcium metal, am I talking about Ca solid or Ca2 plus? Calcium metal. If I'm talking about calcium metal, I'm talking about Ca solid. If I said calcium ion, I would be talking about Ca2 plus. If I say silver metal, automatically you think Ag solid. You do not think Ag plus. If I said silver ion, then it's Ag plus. Silver ion is fixed charge, even though it's in the variable charge region. All right, let's look at section 6.3 here. Compounds made from 2 nonmetals. If there's 2 nonmetals, we call them molecular compounds. Molecular compounds form discrete molecules, like CCl4. What's a molecule of CCl4 called? CCl4 is a liquid. It's a pretty dense liquid. And it's more dense than water. Called carbon chloride or carbon tetrachloride. It's called carbon tetrachloride. Carbon tetrachloride. In this case, if chloride is -1, what would the charge on carbon be? +4. But we don't call it carbon 4. Like, this is just called carbon tetrachloride. What's this one? This is very similar. Carbon tetrabromide. This one, NO. Nitrogen monoxide. Okay. We dropped the mono. We dropped one of the O's, so we call it monoxide. So nitrogen monoxide also has a common name. it's called NO. NO is called nitric oxide. Nitric oxide. NO won the molecule of the year, maybe about 8 years ago or something like that. Have you heard it? Heard about that in Science Magazine? It won the molecule. It's a biological messenger molecule. So NO is really important in biology. Dinitrogen monoxide. Dinitrogen monoxide. Let's write the formula. It's going to be N2O, dinitrogen monoxide. Dinitrogen monoxide is called nitrous oxide. And so we have nitrous oxide, N2O, and nitric oxide, NO. But unfortunately, there are more. There are more, and we've ran out of Aus and Ich. Remember Aus and Ich? Aus refers to the lower charge or higher charge? So this is the common name for this, nitrous oxide. If oxygen is, what's the charge on oxygen? -2, but you always have to be careful with oxygen because oxygen, there's one more charge on oxygen. Do you know what the one more charge on oxygen is? The one more charge on oxygen is this. It's O2, 2 minus, which we call O2, 2 minus, which we call. Yeah, you guys want to get started with the memorization stuff because it's a lot to memorize. Peroxide. Peroxide, each oxygen is a -1. And so we have 2 of them, so the net charge is -2. This is nitrous. Nitrous, usually Aus refers to lower charge. And so if oxygen is -2, nitrogen is +1. Okay? This is nitric oxide. Nitric oxide. If oxygen is -2, then nitrogen is +2. But we also have nitrogen dioxide, so we ran out of Aus-Ich. Aus-Ich only works for 2. And so this one's just called nitrogen dioxide. There's no common name for this one.
So that's not water, it's more H2O.
H2O?
Yeah.
Oh, you mean for the charge?
For the charge.
Yeah, totally. That's how water. That's why water is H2O, because oxygen is -2, hydrogen would be +1 in that case. But we don't call, the funny thing is, when it's a molecular compound, we don't use the rules for ions like this. So we wouldn't call it, the hydrogen 1 ion with the oxide. Same thing here. This is nitrogen dioxide. If this were named as an ionic compound, how would you name this? If this were named as an ionic compound, we would call it. If this were named as an ionic compound, we'd call it nitrogen, but nitrogen has variable charge. And so we call it nitrogen. What's the charge on this nitrogen? Well, if oxygen is -2, that gives us the -4 total charge, and we have 1 nitrogen, which has to have a +4 total charge, which means nitrogen must be +4. So we call nitrogen Roman numeral 4 oxide. If this were named as an ionic compound. If this were named as a molecular compound, we call it nitrogen dioxide. As an ion compound, it's nitrogen 4 oxide. We'll go on here. Sulfur dioxide. What's the formula for that? SO2. Good. Sulfur hexafluoride. The formula for that. SF6. Now, let me talk about the charges on these a little bit more. So on sulfur, if we look at sulfur dioxide, what's the charge on oxygen? We have to be careful because is this peroxide or two oxides? So is it one peroxide or two oxides? One peroxide or two oxides. And so sometimes that requires a little bit further investigation to determine what it is. So for example here, H2O2. We have the same situation. We don't want to be fooled. This could be one peroxide or two oxides. This one requires further investigation. And further investigation, upon further investigation, this is what we get. If this were one peroxide, like this, then hydrogen would be +1. That. If this were two oxides, then hydrogen has to be +2. Have you seen hydrogen +2? No. And so this cannot be two oxides. This doesn't work because hydrogen +2, in fact, hydrogen +2 doesn't exist. We'll see it. And so this has got to be that. In this case, if this were a peroxide, then sulfur would be plus. And if this were two oxides, this sulfur would be +4. It turns out that it's plus 4. It's two oxides. It's not one peroxide. Not always the case, but in this case it is. All right, let's go to the next one. The next one is sulfur hexafluoride. Sulfur hexafluoride would be SF6. Okay, we know the charge on fluorine. The charge on fluorine is -1. Therefore, the charge on sulfur must be +6. Now, there's a pattern in the periodic table I want to talk about a little bit here. You might already be seeing this pattern. In fact, I know some of you are already seeing this pattern here. You're predicting it. Carbon can be 4+ or 4-. Sometimes it's hard to lose all 4 electrons. You know, in fact, losing electrons costs energy. Sometimes it's too much. So, for example, in carbon monoxide, well, let's go to carbon dioxide first. If we look at carbon dioxide, this is carbon with 2 oxygens, and in this case, there are 2 oxides. If there are 2 oxides, that means carbon's got to be
4 positive.
Yeah, 4 positive. Now 4 positive is kind of a high charge, so we use Roman numerals for this. In fact, we use Roman numerals for a lot of these ones. So here, this is carbon with a 4 positive. But sometimes, you know, getting all the way there is tough. And so sometimes we'll have something like carbon monoxide. Carbon monoxide is what would the charge on carbon be here? So oxide is 2-, therefore carbon is 2+, and so it'd be carbon 2. And so that leads to variable charge depending on how completely we combust it. So for example here, carbon can lose 4. If it loses 1, it's like boron. Loses 2, it's like beryllium. Loses 3, it's like lithium. If it loses 4, it's like helium. Because carbon normally has 6 electrons, now it has 2 like helium. Or carbon can gain 4. If it gains 4, it gains 1, 2, 3, 4, it ends up with 10 electrons like neon. And so this is the pattern. Now tell me, is it easier or harder to burn nitrogen? Is it easier to burn nitrogen or harder to burn nitrogen compared to carbon? It's harder. And therefore nitrogen is going to have a lot more variation in the oxides. We call these oxides here. So this is why we have things like nitrous oxide, nitric oxide. It depends on how well you burn the stuff, right? There. But, we can figure it out. Because nitrogen likes to gain 3, right? Or lose how many? Because if it gains 3, then it's like neon with 10. Or it could lose 1, 2, 3, 4, 5. Losing 5 is quite a lot to lose. Yeah? And so it might not lose all 5. So for example, here in nitrous oxide, it just lost 1. This is nitrogen plus 1. In nitric oxide, it lost 2. In nitrogen dioxide, it lost 4. Could lose a 5th, and so there's got to be one more higher. This is not completely, what we call completely combusted. And so that tells us some stuff. So here, with sulfur, what do you think about sulfur? It could gain 2 or lose up to 6. So in sulfur hexafluoride, sulfur hexafluoride, essentially it lost 6. So what comes after hexa? After hexa comes hepta. Do you think sulfur heptafluoride exists? Sulfur heptafluoride. Do you think it exists? No. It doesn't, because this would mean sulfur would have to lose 7. But based on the pattern in the periodic table, it's not going to want to lose 7. It's going to want to lose up to 6. And so sulfur heptafluoride, I don't think, happens. And I told you complete combustion. If we have complete combustion forms CO2. How about, does complete combustion, would it form CO3? I say for sure not. CO3 doesn't exist. Why? CO3 doesn't exist because that means that carbon has to be 6. Can carbon lose 6? If we look at carbon, it loses 1, 2, 3, 4. It's like helium. And then we stop there. And so carbon trioxide, this doesn't happen. But, carbon trioxide doesn't happen, but we had this. We had carbonate. And so the difference is carbon trioxide versus carbonate. Carbonate has these extra 2 electrons that came from something. And so rather than going plus 6, it goes to plus 4 with these 2 extra electrons here. And so we stop at 4. And so we can start seeing some patterns in the periodic table now that'll help us figure out what compounds are possible. So we'll take a break, and then we'll get some more.